This is the third lecture in our Canopy Analysis and Design course. In the previous lecture, we began our discussion on using CE405 to determine the wind load for our canopy. In this lecture, we build on that foundation. Let's summarize what we have learned so far. We can determine the wind design pressure, P, in terms of velocity pressure, Q. Velocity pressure Q is defined using four coefficients: basic wind speed, ground elevation factor, topographic factor, and exposure coefficient. In addition to Q, wind design pressure, P, depends on three factors: the gust effect, the structure's shape and orientation, and its symmetry relative to the wind direction. We covered these coefficients in Lecture 2. Now we turn to the exposure coefficient. The exposure coefficient adjusts the velocity pressure based on the terrain and obstacles around the structure. The rationale for having this coefficient is to ensure that the wind load is accurately estimated by considering how exposed or sheltered the structure is. For example, in flat open areas with few obstructions, the wind can blow more freely and exert greater force on a structure. On the other hand, in densely built-up areas with many buildings, the wind may be slowed down or deflected, reducing its impact on the structure. This is known as surface roughness, the type and density of obstacles that affect wind flow. We use the surface roughness characteristics of the site to determine the exposure of the building to wind. CE405 provides three surface roughness categories: B, C, and D. Let's go through each one. Surface roughness category B includes urban and suburban areas with numerous closely spaced obstructions, such as buildings, trees, and other structures. The terrain is generally rough, disrupting wind flow and reducing wind speeds at ground level. Here is an example of a rough ground surface in an urban setting. This illustration shows a rough ground surface in a suburban setting. This industrial park is another example of Category B surface roughness. This wooded area also creates a rough surface, disrupting wind flow at ground level near the building, so we place it in Category B. Category C, open terrain. This category covers open terrain with scattered obstructions, like open countryside or grasslands with few trees or buildings. Wind speeds are higher than in urban areas because there are fewer obstacles to disrupt the wind flow. Category D. This category includes flat and unobstructed areas, such as mudflats, saltflats, and open water. Wind speeds are the highest in this category due to the lack of obstructions, allowing wind to flow freely. Using the surface roughness category for the site, we can determine the exposure coefficient for the structure. To do this, we must first translate the surface roughness category into an exposure category. CE405 defines three exposure categories, similar to roughness categories, B, C, and D. It's important to keep in mind that while surface roughness categories and exposure categories use the same labels, B, C, and D, they represent related but distinct concepts. Surface roughness describes the physical characteristics of the terrain, whereas exposure categories define how these characteristics affect wind loads on structures. Let's see how exposure categories are defined, starting with Category B. A structure is classified as having exposure Category B if it is less than or equal to 9.1 meters tall, and the ground surface roughness in the wind direction extends more than 457 meters in Category B. Or If the structure is taller than 9.1 meters, the ground surface roughness in the wind direction must be Category B for either 20 times the structure's height or 792 meters, whichever is greater. For a structure to be in exposure Category D, one of the following conditions must be met. The terrain has surface roughness Category D for at least 1,524 meters in the wind direction. Or, the terrain has surface roughness Category B or C near the structure for a distance of no more than 183 meters or 20 times the structure's height, whichever is greater, and the roughness extends in Category D at least an additional 1,524 meters beyond that distance. If the terrain in the wind direction meets either of these requirements, we can classify the structure as exposure Category D. If the exposure category cannot be classified as either B or D, it should be classified as exposure Category C. Now that we've covered how to determine the exposure coefficient, let's apply it to our canopy. The terrain around the bus terminal is mostly flat with a few obstructions. By examining the site image, we see that surface roughness Category B does not apply, as it requires densely obstructed spaces. Our site does not have dense obstructions. Since there is vegetation and a few obstacles around the bus terminal, surface roughness Category D can also be ruled out. The site's surface roughness best matches Category C. As I mentioned earlier, we can determine the exposure category from the surface roughness category using specific criteria. If the surface roughness is Category B, the site can be classified as exposure Category B if either of these conditions is met. However, these conditions do not apply to our site, which has Category C surface roughness. Let's see if any of the two conditions for exposure Category D applies. This condition does not apply, since the surface roughness around the bus terminal is not D, it is C. Does this condition apply? Let's check it out. The bus terminal is 8 meters tall. The greater distance between 183 meters and 20 times the height, 160 meters, is 183 meters. If the surface roughness within 183 meters of the canopy is Category C, and beyond that distance, it remains Category D for at least an additional 1,524 meters, then the structure falls into exposure Category D. However, in our case, the Category C surface roughness extends well beyond 183 meters, making this condition inapplicable. Thus, the canopy does not fall into exposure Category D. Since the exposure category is neither B nor D, it must be C. Therefore, we use exposure Category C to determine the exposure coefficient for the bus terminal. ASCE Table 2610-1 provides the values for the velocity pressure exposure coefficient based on the exposure category. Alternatively, we can use the following equation to determine the coefficient. Z is the height at which wind pressure is to be determined. In our case, it is the height of the canopy, 8 meters. Zg is the height of the atmospheric boundary layer for the terrain exposure, exposure C in our case, which is 750 meters. Alpha is a constant related to gust speed, which is 9.8 for exposure C. Using these values in the formula, we calculate Kz to be 0.95. Now we can calculate the velocity pressure using equation 2610-1. We will continue our discussion on this topic in the next lecture.